So, good afternoon, everyone. I think we should start. Although the attendance today is a bit low, but since it's already 3:03, let's start today's session and let other people join the session in the meantime as well. So, basically, this is the sixth session of ours, and today we will be going deeper into these metal semiconductor junction problems. And let's start. Previously, we had solved the first problem in the previous online class, and today we will be starting with the second problem. This problem statement is like this. It says that we have some arbitrary metal which is deposited on a lightly doped n doped semiconductor, and the work function of the metal is much higher than the work function of the semiconductor. So, which of the following steps will make the metal semiconductor contact an ohmic contact? So, first of all, let's see what kind of contact it will make. For example, it is said that the metal work function here is greater than the semiconductor work function. So since let us see the energy band diagrams for the metal and the semiconductor. If we consider this as the vacuum level, and this is the 1 second, and this is the Fermi level of metal. Krishna Paul, please mute
Yes.
yourself. Please mute yourself. Okay, fine. Now it's fine. So if this is the vacuum level of the
Afternoon,
yes, Krishna Pal,
afternoon, sir.
no problem. Good afternoon. But you mute yourself. Okay. Thank you. So this is if we just consider this as the metal, and this is the vacuum level, and this is the Fermi level of the metal, then the metal work function is given by Q phi m. Now it has been given that the metal work function is uh, higher than the semiconductor work function. So it means that if this is our semiconductor and this is the conduction band, let's say, and it has been said that the metal work function uh, is, although the material is lightly doped, so let me draw it bit closer to this conduction band. So if this is the conduction band of the semiconductor, and if this is the Fermi level, intrinsic one, EFI, let me check, let me see, then the Fermi level, if I consider this intrinsic Fermi level to be in the middle, the Fermi level of this semiconductor due to low doping will be closer to the intrinsic Fermi level. So this is our EFN. Okay, this is the Fermi level of the lightly doped n-type semiconductor. So this is the semiconductor work function Q psi s, and this is the electron affinity. So since it has been given that the phi m is greater than phi s, if this is the what we can say the valence band edge, since it has been given this condition phi m is greater than phi s, we have just drawn the how the materials in the pristine form will, the energy band diagrams in the pristine form will look like. The materials are not in contact, the metal and the semiconductor is not in contact at this stage. So now if we now bring this semiconductor closer to this metal, although this is just for the physical interpretation, we don't do it like this, that we bring semiconductor closer to this. These kind of methods which are used are the fabrication methods. We would say we will deposit the metal on the semiconductor. We will use that kind of a terminology, but for the understanding purposes, let's say that we are bringing the metal closer to the uh, semiconductor. So can anyone answer, since you have gone through the lectures or you have solved the assignment as well, can anyone answer what should happen if I am bringing these two closer to each other? Yes, Aksha.
Uh, Closer to each other, you mean by in band
Yes, I am.
diagram, sir?
Yes, yes. What would happen to this band diagram if I am bringing them together? I am touching metal with the semiconductor. We will be having some interface. So what would happen?
The electrons on the semiconductor side will flow to the metal side. That's why.
Yes, yes, yes.
So we have to increase the amount of electrons in semiconductor side.
No, no, no.
Like
You said correctly, but what would happen to the electrons on the semiconductor side if I am transferring electrons from the
it
semi?
creates the depletion region,
Yes, yes, that's true. So the
forms
electron,
electron
so
hole
the
pairs.
so yes, yes. So the basically the electron concentration. What would happen to the electron concentration? Wait a second. What would happen to the electron concentration at the interface along the semiconductor side?
The interface.
Yes, yes. Interface, by interface, I mean that when I am contacting this metal and this semiconductor, on the left hand side and on the right hand side, I will be having some charge distribution happening. Okay.
The electrons in EFI will flow to Fermi level of the metal, so the
Yes.
band bends
Yes.
and the electrons flows along the bending
Okay.
band bending. That's why we'll get a depletion region because electron hole pairs are generated.
Okay.
That's what
Okay.
I
Okay.
said in the lecture.
Okay. Okay. It's fine. You can anyone else like Mr. Shri Mr. Vinod, or Miss Nityashri. Would you like to add some
Sir,
points?
first of all, the Fermi levels get aligned
Absolutely. Why? Let me ask you one question. Why?
because the excess electrons in the semiconductor will be donated to the metal
And what is the condition for this? When should it happen? When will the Fermi levels be aligned?
at equilibrium.
Yes, absolutely. That's one point we should always remember. Because if we have some bias, then the Fermi levels will be out of equilibrium. Because for the current to flow, we should have some gradient in the Fermi levels. Yes, Mr. Shrihari, you can proceed further.
Since the electrons are flowing from the semiconductor to the metal,
Yes,
the conduction band will move away from the Fermi level of the semiconductor.
absolutely.
Since the electron affinity of the semiconductor is to be constant, since it is the material property,
Mhm.
the vacuum level will also, the difference between the conduction band and the vacuum level will be of the same order, so the difference is maintained. So the vacuum level will bend, the conduction band will bend, and similarly the energy gap between the EC and EV is to be constant.
Hmm.
The valence band will bend, and it is also said that the Fermi level will be close to the valence band. Since it has lost electrons, the Fermi level will move away from the conduction band.
Yes. Okay. So, Mr. Shrihari, as he briefly explained all these things. So, basically, the electron transfer will happen as Aksha also told. So, we will be having some contact like that. We will be having when we this will come closer. The electrons from the n side will we will be devoid of the electrons. I won't say divide, will be a bit divide of the electrons near the interface. So what would happen is that if I align the Fermi levels near the interface, if this is the interface, let me say this is the interface of this metal and the semiconductor, let's say. So since the electrons have been transferred from this what we can say this semiconductor side, so near the interface there will be a bit less electrons as compared to the uh, bulk of the material. So if I say this EC is this is the EC and this is the EFN, let me say, and this is the EV. Since this as Mr. Srihari rightly said that the EG has to be maintained constant, this is EG, this is also EG. So the band bending in both EC and EV would be same. And since the electron transfer has occurred at this interface, there will be we can say there will be some less electrons near the interface on the semiconductor side as compared to the what we can say bulk of the material. So as a result of this thing, we are having this band bending over here, and this is the Schottky barrier height. Okay, actually this junction over here is now the Schottky junction, and this height over here is denoted by the Q5B. This is known by the name of Schottky barrier height. And similar thing happens to the vacuum level as well. The same kind of bending would happen, because we have to maintain this Q chi S, which is the semiconductor electron affinity. This has to be the same throughout, and this is the metal work function. This also has to be same throughout. So you can clearly see this this q phi b would simply be the this q phi m plus what we can say, this q phi m minus q chi s. So simply it would be this q phi m. If I use the energy balance, q phi m will be just the summation of q chi s plus q phi b. Okay, starting from the same points. So if I am considering now these things, and this thing over here, let's denote it by this built-in potential. This is the built-in potential, and let's be clear of the terminology that we will be using. This is the built-in potential that will be generated due to this process that is happening. So we have not drawn any what we can say depletion on the metal side. So can anyone what we can say, can anyone comment on this? Why is there no such thing? Why haven't we drawn the band bending in the metal side? Although if I am having in PN junction, you must have read the lectures, you must have gone through the lectures, you must have seen, if I am having semiconductor on the left and on the semiconductor on the right, I will be having band bending on the semiconductor side on the both the semiconductors, whether it is p type on one side and n type on other side, or whether it is n type of one doping on one side and n type of other doping on other side, there will be some band bending that will be happening on the semiconductor sides. But what are your comments regarding the metal? Why isn't any band bending in the metal? Yes, yes, Mr. Vinod. Okay, Mr. Srihari.
Metal has large energy gap.
Large energy gap. What it has to do with the energy gap?
It's
What
I think
what?
in order of 4 electron volt.
One second. What
So
any? Do you think there is energy gap in metal? What do you mean by energy gap first? Yes, Mr. Vinod. Okay, let us uh, clarify that there is no energy band gap in metal. Okay, okay, Aksha.
Metal has a equipotential surface, therefore the metal band gap doesn't change because only the surface level of metal has the equipotential surface, but metal inside the metal there is no diffusion.
Okay, somewhat acceptable. Yes, Mr. Srihari. I think he is not aware.
Since work function of the metal is a constant value, the band bending will not occur in metals.
Okay.
agreed, sir.
Yes.
Due to work function, which is means not in support in band bending in case of metal, as it supports in case of semiconductor.
So one thing I request you all people, just it's a request to check into this. If you all three check this thing by yourself, you will get the complete understanding of this thing. I won't like to answer this. So I request all three of you to please check this thing so that
Sure.
you develop broader insights into this thing. You will definitely get a lot of knowledge about this metal semiconductor junction if you just try to dig into it, although it's very you can say intuitive. But let me check whether you will see this thing or not, and let me ask you again in the next lecture, in this next live session, whether we have got this thing or not. Okay, so let's leave this thing as it is. Okay, so we were saying that this contact, due to this since this metal work function was greater than this semiconductor work function. By the way, all of you answered beautifully. So there was some intuition behind everything. That's what I liked. You have, whenever you try to answer anything and you have some bit logic behind that, it always gives you some confidence or backing that you are going somewhere in a direction which is oriented towards the physics of device. So that's good thing. Okay, so this now this contact over here is the Schottky contact that has been formed, and we have been told to find that how can we make this contact as ohmic. Okay, only near the junction of the semiconductor. So there is one simple thing. If let me use another color. If this barrier over here is wider, what we can say, if this is wider, then my carriers that are moving, they will have to tunnel through a larger distance. If I denote this by LT, this tunneling distance, as by LT, as we all know, we have seen that when we solve this problem, this particle in a box problem, we saw that this first of all, that there will be, we try to constrain that there will be no electrons outside the box. So but when we proceeded further, we were able to solve, or we were able to see that there is some wave function that exists outside the box as well, due to the tunneling mechanism. And classically this thing was not possible. You have seen the band structures, you have seen this, what you can say, how these electronic wave functions interfere with each other. You have seen that how these electrons, they tunnel even if they have a barrier in front, like I have some wall in front and electron comes in and it can tunnel through. This is a hypothetical example. Okay, this actually it is just vague example to make you understand. If I have some wall and there is some particle which is able to bypass it, which is able to move through this thing, and we call this process as tunneling. So this tunneling process will happen in this kind of a material when we have this metal contacted with this semiconductor, and this contact which is Schottky kind of a thing. So this tunneling process will simply depend on this LT, which is this tunneling distance. Simple, it is simple, because more the thicker this barrier, for example, if I say the more the thicker this barrier is, the lesser probability is that the particle will go through it completely. It will I could say die down in it. It would not have that much of energy, and it would die down in this wall itself if this wall is very thick. But if this wall is very thin, then there is larger probability that the particle will move. So as a particle will completely move through this. So as a result of which, we will try to make this barrier thinner. So this only happens if we dope the material high. So when I dope the material, this barrier will become this triangular wedge. Actually, when deriving this tunneling current, there is one approximation that is used, that is WKB approximation. Although we shouldn't go into that, but let me just say a few words about that thing. That this WKB approximation, it considers this barrier. For example, if this is a barrier, it considers it as a triangular wedge. So if its theta is changing, if its slope is changing, as a result of which this wedge will be having, sorry, different kind of slopes, and it will be becoming steeper and steeper, and this LT will be decreasing. So this LT will be decreasing in this direction, as a result of which the carriers can easily tunnel through this. So they, as it has been written it over here, to make this junction ohmic, we must heavily dope the material by same kind of impurity. So we want to make it more n-type. Okay, we want to make it more n-type. Now this was one brief insight into how we can make this Schottky barrier contact, like sort of an ohmic contact, by highly doping and changing that triangular wedge thing, and changing its what you can say slope, and making it steeper and steeper, and allowing the tunneling distance to decrease. Now there is another problem about this Schottky barrier. So since I was telling you about this Schottky barrier, I was saying that this Schottky barrier, this diagram was in, this band diagram was in thermal equilibrium. Now in this case, this Schottky contact, there is some negative bias applied to this Schottky contact. Wait a second. As a result of which, the Fermi level with respect to the metal will move upwards. Okay, so this results in the, what you can say, this results the process to be uh, go out of equilibrium, and there will be some current in this kind of a case. So if we are applying some negative bias on the metal, and we have been told to comment on the, what we can say, peak electric field and the width of the depletion region. So if we simply go by this Schottky barrier contact, when we solve this Poisson's equation for the electric field, considering the this constant doping Nd, you must have seen that you got this electric field as a function of x. It was some number q by Nd, and divided by epsilon x minus xt kind of a thing that you got for the doping, which was the doping was at that time, the doping concentration was constant. Okay, so for that thing you solved the Poisson equation. You said that for one dimension, dE by dx is equal to rho by epsilon. Okay, you just found the rho to be equal to q times the doping concentration that had used, q times Nd, and when you solve this, you said that we will integrate it with respect to x, and we will get the electric field in this region, and you got that thing to be as a function of x minus xt. Xt we got by using the boundary condition. We said that outside the, wait a second, outside the depletion region, this electric field will be 0. So as a result of which, we got the condition that this electric field was somewhat some expression like q times Nd by epsilon s x minus xt, where this xt is the depletion width. Now we have been told to, wait a second, okay, okay, now we have been told to find the what happens to the peak of the what we can say, the magnitude of the electric field, and with the and the width of the depletion region. So this width of the depletion region, you must have solved then this Poisson equation, and you must have used this you must have used its Poisson form. This was the, what we can say, the when you must have used that electric field is minus dV by dx. You must have integrated it again, and you must have got the built-in potential. So this built-in potential, and when we solve for that xt, which is the depletion width, this is the depletion width. Okay, depletion width, and we know that the maximum electric field would be at the junction. So it would be simply E max, maximum electric field magnitude would simply be E times Nd, and at junction x is 0, so epsilon s xt. So this is the maximum electric field value that we will be having, and it depends on what? It depends on this XD, which is the depletion width. So whatever happens to this depletion width would happen to the maximum of the electric field, because we know for a particular material this Q and epsilon S will be constant, and this Nd is the doping concentration that we have used a priori, and now this XD is the only thing that we need to check what happens to it with the bias. So now this XD is simply 2 times epsilon S phi Bi, where this phi Bi is the built-in potential, minus Va. Va is the applied bias, okay, by Q and D. Now if I consider now the thermal equilibrium, this has been said that the material is in equilibrium, okay. When material is in equilibrium, applied bias Va is equal to 0 simply, okay, when in equilibrium. So when I am in equilibrium, the Va is equal to 0, and this Xt would simply be having some value which is a function of phi Bi. So Xt1 will be 2 times epsilon S phi Bi by Q and D. Now when this negative bias is applied, when this Va is negative, yes, when this Va is negative, this Xd2 is simply 2 times epsilon S phi Bi minus of minus Va, which would become, if Va is now minus Vr, which is the reverse bias kind of a thing that I have denoted with. So this is my plus now, and this is Q times Nd. So you can clearly see this Xd1, it has this dependency on the phi Bi, and Xd2 has this dependency on the phi Bi plus Vr. So clearly this Xd2 is greater than Xd1. So what we can say, that this depletion width has increased. This depletion width has increased, okay, as compared to the equilibrium. And what has happened to the electric field? Since this Xt has increased, the electric field will it would also increase. So this simple solution for this would be that both would increase when applying the negative bias to this Schottky contact. Now there is some another problem which is associated with this metal semiconductor contact, and this problem is also related to our understanding of how we can draw the band diagram and how we can manipulate this band diagram to get the to obtain the relations of various variables using the energy balance. So energy balance, as I had previously also said, that it is really important to solve the energy band diagram, keeping in mind the various energies that are present in this energy band diagram, and how we can use them to manipulate or obtain the values which we desire. And we had said that at all the things in the semiconductor device physics happen at the interfaces. As we have seen in the bulk of the, for example, material, there is nothing interesting physics happening, but at the interface every sort of important physical aspects are governing the device performance. So this chromium, we have been told that we have to consider this chromium, which is n-type, and we have to consider the semiconductor metal junction, and this semiconductor is doped with the concentration of 10 to the power of 17, and the Schottky barrier height is being given to be equal to, we have to calculate the Schottky barrier height and the built-in potential, and we have to use the parameters like the work function, electron affinity, band gap, and NC. So we have seen that since this metal work function, we have been given this Schottky barrier height is to be found, and the material is N-type. We will simply draw the energy band diagram that we had previously drawn for the Schottky contact over here, this band diagram. So it would simply be, if I draw it again, it would simply be this EFM or EF now, this Fermi level, and this is the Schottky contact. Okay, this is the conduction band edge. Okay, this is the built-in potential. Fine, this is the Schottky barrier height Q phi capital B, and this is the vacuum level. This is the semiconductor electron affinity. This is the metal work function. Okay, now we have been told to, what we can say, uh, let me complete it by drawing this valence band as well. So this is the valence band. So this EC minus EF is simply Q phi F. Okay, this is simply Q phi F in the bulk of the material. So we have to first find the Schottky barrier height, and we know this Schottky barrier height is simply Q phi M equal to Q chi S plus Q phi B, or this phi B is simply phi M minus phi S. Sorry, phi M minus chi S. Okay, chi S. Yes, phi M minus chi S. So phi M was given to be equal to 4.5 and chi S is given to be equal to 4.05. So it would be simply 4.5 minus 4.05, and it is 0.45 electron volts. So this is the Schottky barrier height that we will be obtaining for this. Now, if I now have to solve for this thing, which is this built-in potential, now let's use the energy balance again. We can say that this simply, this thing over here, this Q phi B, is simply equal to Q phi Bi plus Q phi F. Okay, this is simply the energy balance. The energy is equal to the energy on the left hand side is equal to the energy on the right hand side, or the total energy going through a loop is equal to 0. So this would simply mean this Q phi Bi, or this phi Bi is simply Q phi B minus Q phi F, or simply we can say that phi Bi is equal to phi B minus phi F. So we need to find this phi F, which would be simply given by the expression, which is a function of the doping concentration of this material used, and the what is the concentration at the conduction band edge, and the concentration at the conduction band edge is given to be equal to 2.82, and the doping is given to be equal to 10 to the power of 17 per centimeter cube. So we can easily obtain this phi F. Phi F is simply EC minus EF, is KT ln of NC by ND. Okay, so it would simply be 0.026 ln of NC. NC is 2.82 into 10 raised power 19, 2.82 into 10 raised power 19 divided by ND, 10 to the power of 17. So let us solve this, and we will obtain the value for this phi F. Okay, so it would be 2.82 into 10 raised power 2, simply ln of 2.82 into 10 raised power of 2. It is 5.64 into 0.026, which is 0.15. So this phi f came out to be equal to 0.51 volt. Okay. Now this thing phi bi uh, can simply be written to be equal to, I have written this as q phi b. Q phi b is 4.45. Now for this phi bi, this phi b will be 0.45 volts minus this phi f, which is 0.15. So I have used this equation A over here. So this is 0.445 minus 0.15, which is 0.3 volts, and this is the built-in potential that we will get. So we have got this to be equal to 0.45 and this to be equal to 0.3. So 0.45 and 0.3 is the option B. So option B is matching our choice. So we would go with the option B. Now there is another problem which is of a similar kind, but only the thing over here different. The only thing that is different over here is this Na. Now in this case we are having the same parameters, but only one thing that is different over here is this material now is doped with the accepted doping concentration of the power of 10 to the power of 17. So now we have p-type doping in this material, as a result of which let me draw the band diagrams when they are these materials are far away from each other. If this is the vacuum level throughout and this is the metal work function, okay, this is the metal work function which was given to be equal to 4.5. Let me write it down, 4.5 electron volts. The electron affinity is 4.05, so it would be somewhat here. Let me say it is 4.05 and it is somewhat closer to this thing. Wait a second. So I am again saying that if you are able to draw these energy band diagrams, you will be able to understand every aspect of this metal semiconductor junction. Wait a second, let me draw it again because it looks like that there is some slope in it, but in reality there is no slope. It might look that these are a bit closer. So if this is 4.05, okay, then if this is the valence band, okay, and since this is the conduction band, okay, and the material is what you can say, material is n p-type doped, where do you expect the Fermi level? So let me ask you this thing, and also the band gap is going to be 1.12. This band gap is going to be 1.12 electron volts. So I am asking you people, where do you expect the this Fermi level to be for this n type of material? So obviously, sorry, p type of material. So obviously it will be closer to the valence band. So if I say it is over here, this Fermi level. So if it is over here, let us say, I drew it on purpose that I said that this Fermi level is less, the Fermi level of the semiconductor is less than, is much more than the in magnitude it is much more than the Fermi level of the metal, because I know this gap, total gap over here is the band gap, it is equal to 1.12 electron volts, okay, and its half will be 0.56. So if I consider the intrinsic Fermi level over here, it would be 0.56, okay. So this is one thing that I have interpreted from this thing. So if I add 0.56 with 4.05, I would simply obtain the value of this EI, where this EI is located. So it would be simply 4.61 electron volts. So since this EI is at 4.61 electron volts and EFS, the Fermi level of the semiconductor, has to be below this EF, this intrinsic Fermi level, EFI or EI. So it means that this metal work function phi m is less than phi s, because it is just phi m is just 4.5 electron volts, and phi s, we, since we have not calculated it yet, and phi s has to be greater than this value 4.05 plus 0.56, because this band gap is 1.12 electron volts, and also the intrinsic Fermi level, this Fermi level of this semiconductor on the p type has to be lying below the intrinsic Fermi level for p-type material. So this clearly means that this type of a contact would be ohmic contact. You have seen that this phi m, if this phi m is less than phi s for this material, this n-type material, then it is ohmic contact for n-type material. But over here it is p-type material. Okay, so since it is p-type material, everything will be now reverse. So phi m, when phi m is less than phi s, for p-type material it will be now the Schottky contact. Okay, because you have to consider opposite mechanism of the electrons. For the electrons, we had said that if phi m would be less than phi s, we will be getting ohmic contact. Now the transport mechanism, we can say, is the complement for the holes. So as a result of this thing, we will be having the opposite things that are happening for the n-type and for the p-type. So you can clearly say or simply say that when this phi m is less than phi s, for the p-type material we will be having Schottky contact. Okay, and for n-type material, if I am having phi m which is less than phi s, I will be having ohmic contact. So now if I draw the energy band diagram for this thing, the when the both the materials are closer to each other, it would be EF, and since the electron transfer has occurred from the, you can say, at the interface from the metal to the semiconductor. Metal, remember, has a large number of electrons. Okay, as a result of which now the electrons in the at the interface near the semiconductor side would be more as compared to the bulk, as a result of which we will be having some bending, like you can say like this. Since this thing has more electrons, okay, since this thing has more electrons at the interface than the, you can say, it has more electrons than at the interface than the bulk. So we can see, you can denote this by q phi f, and this is our Fermi level, and this is the valence band edge, this is the conduction band edge. Okay, this is the band gap, total band gap of material, which will remain constant throughout. And if this much amount of band bending has happened, so this is the vacuum level, you can say. So it would be like this, vacuum level will go like this. So this electron affinity for the material would simply be q chi s, and it would be constant for the semiconductor, and this phi m is the metal work function for this, what you can say, this metal work function, and this Eg, this is this now the Schottky barrier in p-type material. This is the Schottky barrier that is being offered to the holes. So if we now see the energy balance for this kind of a thing, you would clearly say that this q phi b plus this q phi m is simply equal to this thing over here, which is q chi s plus Eg. We have simply used the energy balance. Now this, if this thing is equal to this thing, we know all these values, we can simply say this phi b is simply equal to this, since we have to deal in the voltage volt units, we will say that we have gone about this thing by they were doing for the values of this phi m and chi and eg. So this chi s was equal to 4.05 electron volts, or if I divided by the electron by q, it would be simply 4.05 volts. And considering the potentials only, okay, I am not considering the uh, this thing now. So this thing, let us deal in electron volts. Let's deal in electron volts itself, so that we don't get confused. So this is the in the electron volts. So the band gap we need to find in electron volts. This is the energy. Let's not deal in voltage, volt units. We'll deal in energy only. This has the unit of electron volts. Chi s is given, q chi s is given to be equal to 4.05 electron volts, and Eg is given to be equal to 1.2 electron volts, and phi m is the metal work function, which is given to be equal to 4.5 electron volts. So if I solve for this, I should get 1.2 minus this thing. So it is simply minus 0.545, and it is simply equal to 0.67, okay, electron volts. So we have got this Schottky barrier for the p-type semiconductor. Now there is another part of this. We have to find this built-in potential. We will use similar kind of a thing for the built-in potential over here as well. We will say that this built-in potential is simply equal to phi b. This is the built-in potential phi bi. Q phi bi is the summation of this thing is q phi b is the Schottky barrier. It is just the sum of q phi bi and q phi f. So if I solve for this, we would simply say that phi bi is phi m minus phi f, similar to that of the n-type Schottky. What has happened to this? Okay, what has happened to it? Oh, let me write it again. So it was like this is the, what we can say, phi bi is simply phi m minus, sorry, not phi m, it is phi b minus phi f. So this phi f, we will find it to be from this energy band diagram relation. This phi f is simply EFP minus EV. So EFP minus EV is simply KT ln of, actually it is KT by Q ln of NV by NA. So it is NV, the NV value is given to be equal to, let me check, okay, it's over given over here, it is given to be equal to 1.83 into 10 raised power 19. So it is 0.026 ln of NV is 1.83 into 10 raised power of 19. It was given. Na was 10 to the power of 17. So it is 10 to the power of 17. So let's solve for this and obtain the value of this phi f. So let's solve for this. 1.83, it would be simply ln of 1.83 into, it would be 5.29 into 0.02. It would be simply equal to 0.14. Approximately it will be equal to 0.14. Okay, so we have obtained the value for this, it to be equal to 0.14, and the built-in voltage would simply be phi b, which is 0.67 minus 0.14. So it is minus 0.67, which is 0.53. So this phi bi is simply equal to 0.53. So we have to check the options, which is this we have got this option 0.67 and 0.53. So we have obtained both the barriers, the Schottky barrier height and the built-in potential that would be uh, uh, arising in this p type of a material when we are doping it with the concentration of 10 to the power of 70. Okay. Now there is another problem. It says that I have this n-type semiconductor, which is chromium. Chromium is the metal, and I have the n-type semiconductors of silicon, and it is given in the question 4 as a same material which is given in the question 4, and we have to calculate the following quantities when the junction is in the reverse bias. We have to calculate the depletion width and the electric field at the metal semiconductor interface. So this depletion width we have seen when we were discussing this, we saw that this depletion width is simply uh, obtained when we solve for the Poisson equation, and when we use this Gauss law and then we go for the Poisson equation, we obtain this xd to be equal to 2 times epsilon s phi bi minus va by q n d. Okay, so this is the simple expression that we will get, and we have to find this VR, this reverse bias voltage is going to be equal to it is going to be equal to what we can say minus 5 volts. So VR is equal to minus 5 volts since it is given it is in reverse bias. So this is the VA value. Okay, and we have phi bi that we have obtained from the question number 3, question number 4. So let's check this question number 4. Phi bi value, phi bi is 0.3 volts. Okay, so this phi bi is simply 0.3 volts, and if I solve for this xt, it would be simply 2 times epsilon s. Epsilon s, this is this silicon material, and I think we must have been given this dielectric constant. Its dielectric constant is 11.9. Okay, so let me solve for this. So 2 times 11.9 into, since we are dealing in centimeters, it would be 8.85 into 10 raised power of minus 14. Yes, it's minus 12, but since we are dealing in centimeters, we will say it is 8.85 into 10 raised power minus 14. Phi bi is 0.3 and va is minus 5, so it would be plus 5, and q is 1.6 into 10 raised power minus 19. Nd is simply, let us check, nd is 10 to the power of 17. So if we solve for this, let's solve for this, it would simply be 9 into 8.85 into 5.3 divided by, wait a second, divided by 1.6, and this is 697.7. This will go up, it would be 14, this would be minus 2, and it would go up, it would be plus 2, it would be plus 2, and it would be minus 12, and it would be minus 6, and 697 under root is 697 under root is approximately 0.226 it is. So it is coming out to be equal to, now let's do the units in meter, it's coming out to be equal to 0.26 micrometer. This is the depletion width. Since it is given in the micrometer only, we have converted the units from centimeter to the uh, meter again. So this is the depletion width that we have obtained. Now for the peak electric field, this electric field at the metal semiconductor interface in the units of now volt per centimeter. So it is in now units of volt per centimeter. So the electric field will simply be, this electric field at x equal to 0 would simply be equal to q times nd xt by epsilon s. Yes, this is what we have obtained over, I think, in this expression. Yes, x minus xd q times nd as xt by epsilon s. So this is the peak electric field at the interface that is occurring. It would be simply now 1.6 into 10 raised power minus 19, nd is 10 to the power of 17, and this thing is 0.26 micrometer, or simply 0.26 micrometer is 10 to the power minus 4 centimeter, divided by epsilon s. Epsilon s is 11.9 into 8.85 into 10 raised power minus 14. This is the value of epsilon naught. Okay, so this will be now in the units of volt per centimeter. So if we solve for this, it is simply 1.6 into 0.26. Yes, it's 0.26 divided by 11.9 divided by 8.85. It is 0.00395. So let us convert its units. It is 3.95 into, it would be 10 to the power of 4. Sorry, not 10 to the power of 5. One more 1 is there. Okay, one more 0 was there. So it is 10 to the power of 5. 3.95 into 10 to the power of 5 volt per centimeter. Okay, I guess it is 0.26, and 0.26 is the only option A, and we have got the value for this electric field to be equal to 3.95 into 10 raised power 5, which is also there. So both the options are matching. Now we have been given same kind of another problem. We can say that this on this semiconductor, metal semiconductor junction, which is in this question 4, and now we have been told to obtain the junction capacitance per unit area in this problem, and the potential drop across the semiconductor. So now we are, when we are in thermal equilibrium, again let me reiterate on this point. At thermal equilibrium, this potential drop across the semiconductor is simply built-in potential. Okay, that we have seen that under the thermal equilibrium, whenever we draw this, we saw this potential drop across the semiconductor is simply this q phi bi. So this is the built-in potential, and for problem 4, this phi bi is 0.3 volts. So let me check again whether it's 0.3. Wait a second. Yes, it is 0.3 that we had taken. So that we had obtained, it is 0.3. Now if I apply some this external bias, if I apply this external bias, what would happen is this VA, this external bias, it will appear across the semiconductor, because this drop uh, across the metal will be very less, so it will be negligible. So we can consider whole drop happening, the whole drop, voltage drop that is occurring, it is occurring in the semiconductor side. You have to look into this, as I have told you what is happening at the metal interface or the metal side. You have to look into this. So this now I can consider this, now this voltage drop across this semiconductor now is simply phi bi minus of Va, which is this reverse bias voltage. So it would be simply zero point 0.3 minus of minus 5 is plus 5, it would be 5.3 volts. So this is simply 5.3 volts. So the drop across this what we can say across this semiconductor is, the semiconductor material is 5.3 volts now. And we have considered the negligible drop in the metal side. This has to be true. So now if we have to find the junction capacitance, this, wait a second, this junction capacitance is simply equal to Cj is equal to epsilon s by xt. So depletion capacitance, it is simply this junction capacitance per unit area, I would say per unit area rather, because I have not taken epsilon a by d in this, I have normalized it with respect to the area. So this depletion capacitance this is the depletion capacitance per unit area in the reverse bias. Okay, Cj, this junction capacitance. So this xd we have found out it was equal to 0.26 micrometer, and epsilon s is simply 11.9 into 8.85 into 10 raised power of minus 14, and this xt is 0.26 into 10 raised power minus 4 centimeter. So if I solve for this, it would be of the order of 10 to the power of minus 10. Simply it is 11.9 into 8.85 divided by 0.26. It is 4.05 into 10 raised power minus 8. So it is 4.05 into 10 raised power of minus 8 farad per centimeter square, since this was in centimeter, and above we had epsilon s in units of farad per centimeter. So this is the value we have obtained. This simply means this is for 4.05 into 10 raised power minus 8. So 5.3 option C is matching, but it is 40 point. We had obtained it equal to 4.05. So is there any, okay, capacitance per unit area in nano, it has to be in the units of nano. Okay, so if it is in the units of nano, it would be 4.40.5 into 10 raised power minus 9 farad per centimeter square, or 40.5 nanofarad per centimeter square. Okay, so the option C is the correct option. Now I had just one question about this thing. So what do you think this junction capacitance over here, considering the relation over this thing, this q by md xt, okay, so 2 times epsilon s vbi, okay. So let me ask you one question. So what do you think, uh, what can be the implications of this thing, this Cj that we are seeing over here, this Cj, this Cj is some capacitance that we are getting, and this capacitance is, it is dependent on, depends on xj, sorry, xd, okay, or xj is also sometimes written. So this is the depletion width. So can anyone comment or say what could be its, what you can say, practical application or usage of this capacitance that we are obtaining over here? So do you
Parallel
know?
plate capacitor, sir.
Yes, parallel plate capacitance. Absolutely, Mr. Shiriari. So we have always seen that that in this when we design, for example, if we are designing or building some circuit, and we have to use capacitance, for example, in that circuit. Wait a second. We have to use some capacitance in that circuit. We cannot use the parallel plate capacitor. For example, I will have some metal over here and another metal over here and bring some dielectric in that and integrate it on some IC. This is not how it is done when I am designing the circuits, because I need to have all the things, all the components. I will try to use the silicon itself or the material that I am fabricating. For example, if I have to use the resistance, I will just use a bar of silicon, for example, or any other material. Similarly, if I have to use this same material as a capacitor, I will do something like this. I will just have this same material which is deposited, and I will just deposit some metal contact to it, and we will use this reverse bias kind of a thing in order to modulate the capacitance. So we will be having this, what we can say, the capacitance that is modulated by the change in the depletion width through the external bias. Since this XD, it depends directly on this root of this VR, reverse bias. So if I change this VR, I am changing this junction capacitance. So what I am getting is this: I am getting some control over the, I am getting some control knob over the capacitance. So I have obtained this, what you can say, this junction capacitance as a means to be used as an component in the integrated circuit. So you must have seen that this voltage dependent capacitance, they were used in the, you can say, the trans receivers kind of things. So this is one of the practical applications of this thing, that by just tuning this voltage, external voltage, by the knob, by some kind of a knob, we are able to change the capacitance. So this is one practical application for this thing, that having the one material, I can build the resistance, I can build the capacitance, okay, just by having some different metal contact. And this results in the, okay, what you can say, ease for the device people or the fabrication people or the circuit people, that they are able to get all the components from just the same kind of a material. We do not have to use the external lossy capacitors or bulky huge capacitors. We will get the capacitance from the material or the semiconductor material that we are using itself. Now this there is another problem which is related to this Schottky contact. This there is some this Schottky diode, what you can say, we have this Schottky diode, and we have to obtain this relationship of this built-in potential and the donor concentration, and the capacitance of the Schottky diode is given by some relation which is 1 by C square equal to A minus B V, where this V is the applied voltage, okay, and A and B are some constants. Now this is some good problem, and these kind of problems help you to interpret, or you can say help you to obtain the what you can say, the relations, or what you can say, or the uh, physical aspects of the things that you obtain in the material systems. For example, I have been given some capacitance as a function of voltage. I will be asked to find the built-in voltage from the same thing, and I will be asked to find the doping of the material. Similar kind of techniques are used by the people who characterize and model the materials. You must have heard that we model the materials. For example, I have to design some circuit. The material behavior has to be represented in some form of equations, you can say. So when I am given some experimental data and I am trying to characterize it, I am trying to model it. So I need to have some information about its, what we can say, doping, about its threshold voltage. So these kind of things, the built-in voltage, so these kind of things or these kind of mathematical manipulations help you to understand how you can obtain those, for example, built-in voltages or the threshold voltages or the doping or the thickness of the oxide, etc., by just doing the back calculations. So this simple problem over here says that I have some capacitance which is a function of this voltage, and we have been told to find some quantities. Let us find those quantities, which is the built-in potential and the this donor concentration. So these are two properties. One is the doping concentration that I need to find for a particular material, and another is the, what you can say, this built-in potential. You can consider that I have fitted the material by using, for example, I have fitted this capacitance curve by using two parameters, which is A and B. Now I am being told to find the doping that I had used to dope this material and the built-in potential that was present in this material by just doing the back calculations. So basically these A and B are some fitting parameters that I had modeled my data with. So now this 1 by c square is equal to A minus B V, and this XD, we know this XD is the depletion width. Since this capacitance, this junction capacitance is simply, this capacitance is simply epsilon s by xd, and this xd is simply 2 times epsilon s phi bi minus v. Okay, v is the applied bias, divided by q times nd. Okay, now this is a junction capacitance or this capacitance per unit area. Now if I have the area as well, the total capacitance is simply equal to epsilon s A by xd. So this is as simple as that. Now let's put the value of this xd over here. It is epsilon s A by, so this is 2 epsilon s, and this is phi bi minus v. Okay, and this is root of q and d. Yes. Okay, this epsilon and this epsilon, its square root will go, so we will be having root epsilon in the numerator, so it would be like this. This c will be simply equal to A times q times and d times epsilon, which is under the square root, divided by 2 times epsilon s, phi bi minus v. Okay, so if now I square this thing, it would be simply ct square is equal to a square q times nd epsilon s. Sorry, where is this epsilon s come from? Okay, have I done something wrong? Let us backtrack everything. 2 times epsilon s phi bi. Okay, so this epsilon s is not there because it got cancelled with the root. Okay, so this epsilon s is not there, so it is simply phi bi minus v, simply. Yes, I think now it's correct. By 2 is also there. Yes, 2 is also there. So now if I do the reciprocal of this, it will be 1 by ct square. It would be 2 phi bi minus 2v divided by a square q and d epsilon s divided by a square Q and D epsilon S. Yes, this is it. So is there any mistake over here? So I don't think so, there is some mistake. So now if I compare it with this thing, 1 by C square is equal to A minus BV. So this is the capacitance relation that I had modeled this thing with. So this is this model relation. I need to find these parameters, this fitting parameters I have found out from these fitting, sorry, from these fitting parameters. I now need to find this doping. I have been given these values. So if I compare this thing over here, it is simply A is equal to 2 phi bi by A square Q and D epsilon S. Okay, yes, this is the A. So if this is A, so I can simply say now this B is simply equal to this thing, since this BV is equal to 2 A square Q and D epsilon S. So it is simply equal to, B is simply equal to 2 by epsilon S A square Q and D, or simply ND is equal to, since I know this B, this ND is equal to 2 by epsilon S A square, where A is the area, Q times B. So now I have obtained the value for this doping that I have used by just knowing this fitting parameter, this parameter B. I know this. I have some relation, I had some relation between the capacitance and voltage, and I had fitted it with some equation of the linear equation of the form of A minus BV, and I had obtained that B value and the A value. Now from that B value I can approximately infer the doping. So this I had obtained from fitting, or some relation obtained from fitting the CV curve. Okay, CV curve. Fine. Now this ND is simply has been obtained, and this A is simply now equal to, or this phi BI is simply equal to, what you can say, this is equal to A square, simply it is equal to A times A square Q times ND epsilon S, okay, divided by 2. Okay, this is our phi bi. So we have obtained both the things. Now phi bi can easily be obtained as we know this nd. Now this nd is some function of, what you can say, some function of b. We know b, as a result of which we now know this phi bi as well. So this is simple, that we have obtained this phi bi and this nd. This phi bi is simply equal to, it was simply equal to 2 it was equal to a square q by nd epsilon s, a square q by, so I think this thing, let me tick it first and then check. So this is simply 2 by epsilon s a square qb, 2 by epsilon s qb a square. Yes, it is same option. This is a square q and d epsilon s, a square q and d epsilon s, a square q epsilon and ds by 2. Yes, absolutely. So this option B seems to be the correct option, and we have obtained the bus by just fitting this some CV relation that we had obtained. We have used some fitting parameters and B, and fitted the data simply by or using different combinations for those values of A and B, and as a result of which now we were told to do the back engineering. Earlier we were given the value of ND, we were given the value of, for example, the conduction band edge and the Fermi level difference, so that we can find this phi f, the difference between EC and EF, as a result of which we were able to find the built-in potential. But this kind of a problem now is the reverse engineering kind of a problem. We can consider that I was given some wafer, not wafer, let me consider, I was given some semiconductor bar, and I was told to do the capacitance measurement for that, and I applied some bias randomly, and I got some capacitance values, and I you got these values, these capacitance values, and these for the particular voltage values. I used two columns. I did this thing that I had two columns. On one column I had this capacitance thing, and on another column I had this voltage thing, for example. And then I simply tried to map these capacitance and voltage relations by using some equation. So the equation over here was A minus BV, though, so it was a linear equation for the as of a function of V for this C square, 1 by C square. So as a result of this thing, we got these fitting parameters A minus B, B where B was the slope and A was the intercept. So from those fitting parameters, now we backtrack and we obtain the doping and the built-in potential. So this kind of a problem is quite interesting when you are doing the reverse engineering, and these kind of problems are mostly you can say counterintuitive for some of the reasons, and for many of the students these are some counterintuitive. Although in this problem it was clearly given, or and it was easily interpretable that you have to do it like this, but sometimes they it might have been given that we might have been given some capacitance plot for the PN junction, and we would have been told to find its what you can say built-in voltage by just interpreting the slope of the material, how it would intersect the material at material, for example the CV curve we must have obtained as a function of voltage, and as a result of this CV relation, where would it intersect? For example, it intersected the x-axis or the voltage axis at some point, and that point would correspond to some value for a PN junction, and that value simply will be this built-in voltage. And similar is the case over here when we are what we can say interpolating this equation. We will see that at some bias you get this value to be equal to this capacitance value, this capacitance value. You obtain it, and by interpreting that CV plot, and you obtain the built-in voltage corresponding to that value. So now this there is some another problem which is related to this metal semiconductor. I guess I have one more problem. Yes, so this is also related to this metal semiconductor, and this problem over here states that I have n-type material which is doped with 10 to the power of 15, and now this material is kept, this metal contact is kept 5 volt below the semiconductor. Okay, and which what is the electric field in the semiconductor at a distance of 1 micrometer, and the temperature is given to be equal to 300 Kelvin, and the effective density of state at the conduction band edge is the 2.82 into 10 raised power 19 per cubic centimeter, and rest of the parameters are also given. So now this we can simply say this electric field relation that we have obtained by solving our most loved equations, the Poisson equation and the Gauss law. So when we have obtained these value, this electric field as a function of x for the what we can say constant or a uniform doping, you must have seen that this was equal to q times nd by epsilon s x minus xd. Xd was the depletion width. So this xd, when we solved this Poisson equation, we obtained it as a function of Vbi to be equal to 2 times epsilon s phi bi minus Va. Okay, so this is minus Va divided by Q and D. Simply. Now this electric field now is a function of x, and we have to find this xt first in order to obtain the value of this electric field within this depletion region, okay, which is 1 micrometer. So first of all, we must solve for this, what we can say, this phi bi. This phi bi is simply the built-in potential, and it is phi b, which is the Schottky barrier height, minus this kT by q. Since we have done it many times, now let us write it directly. So this is kT by q ln of Nc by Nd. This phi b is simply the metal work function minus the electron affinity Schottky barrier height. So it is simply phi m minus chi s. Okay, this is minus kT by q ln of Nc by Nd. Okay, now if we see this value is 5.1 for the phi m. For the silicon it is 4.05. So it is simply, this is simply equal to, let's add some slide, it is equal to 5.1 minus 4.05 minus 0.026. Since the temperature is 300 Kelvin, kT will be 26 milli electron volts. So this is a 0.026 electron volts divided by Q will give me it in volts. So it is ln of Nc. Nc is going to be equal to 2.82 in raised power 19, and Nd is 10 raised power 15. So it is 2.82 into 10 raised power 19 divided by 10 raised power 15. So it is simply 10 raised power 14. So it is 10 raised power 4. So let us simply say ln of 2.82 into 34 into 0.026, it is 0.266. So plus 4.05 minus 5.1, it is coming out to be equal to 0.78. So it is coming out to be equal to 0.78. Okay, so this is our phi b I. Now this electric field at x equal to 1 micrometer. 1 micrometer is simply equal to Q times Nd. Q times is 1.6 into 10 raised power minus 19. Nd is 10 raised power 15. Epsilon s is 11.8. It is going to be 11.8 over here into 8.85 into 10 raised power minus 14 farad per centimeter, and this is 1 micrometer. Since it's x minus xt, it is 1 micrometer, which is 1 into 10 raised power minus 4 centimeter, minus xt is simply 2 times epsilon s is 11.8 into 8.85 into 10 raised power minus 14 into this thing has to be whole multiplied by phi bi plus the reverse bias voltage, which is 0.78 plus 5. This has to be divided by, simply divided by q times Nd. So it is 1.6 into 10 raised power minus 19 into 10 raised power of 15. So it is 10 raised power of 4. So let's solve for this. So let's leave this. So because it's a long calculation, so let's leave this. It will unnecessarily take much time to solve this. So this is how this concept is for this electric field. So this is the electric field expression as a function of the xt. So you will be getting some electric field at the distance of 1 micrometer from the we can say interface. Okay, this is from the interface, basically the electric field at 1 micrometer from the interface. Now this there is some another problem about this metal semiconductor junction, and we have seen this thermionic emission and the tunneling current. We have seen this tunneling current more rigorously, that how this depends on this tunneling, this triangular barrier, and how at the junction it increases the tunneling of these carriers from the one side to the other, as a result of which we will be having increase or the enhancement in the tunneling current. So it is quite simple that how this increase in doping decreases that uh, uh, LT, that tunneling distance, as a result of which we had more and more tunneling current. So this is also true that diffusion transport through a junction is negligible in reverse bias. And thermionic emission, we know this thermionic emission is simply it increases with the temperature, because KT, we have this KT kind of a thing. As the temperature increases, we have more and more number of carriers which are able to move over the barrier. So when you will solve for this MOSFET, you will see that how the carriers, or even in this case for this metal semiconductor junction, how the carriers move over the barrier. Because when we have the Schottky barrier kind of a thing like this, some of the carriers can move above this barrier. They can move one. There are two, basically there are two transport mechanisms that are happening broadly. I would say there are two kind of transport mechanism. One is the tunneling. The carriers come from this side and they directly tunnel through this barrier kind of a thing. And another mechanism is that there will be carriers which will be having much higher energy than this barrier, and they will just hop over this barrier. Okay, they will just move from this side to this side because of the greater energy or the large energy they are having as compared to the barrier. So all the three options below are correct. And this thermionic emission, there is another statement about this thermionic emission. This thermionic emission, basically it depends on the barrier height, because if we are having more higher the barrier, as a result of which I will be requiring more energy to overcome this barrier. I will be requiring large amount of KT to move above this barrier. But if I am having lesser barrier, I will be having more carriers that can move over the barrier from the metal to the semiconductor side. So it just depends on these two things. It does not depend on the band bending, because we have this barrier height, which is the major governing factor, and the KT, which is the energy of the carriers that are trying to move over the barrier. So this option, thermionic emission, depends on the shape of the band bending inside the semiconductor, is incorrect. So we will select this option. So it is, we had to select which of the following statement is not correct. So basically the thermionic emission will only depend on the barrier height and the temperature. So it is the over the barrier transport that is happening. Now let's move to the PN junction. So we have seen the similar kind of a problem what I was saying in the previous slide, how this capacitance, they can help you to obtain the when I am given some capacitance relationship, how I can obtain the doping values or this built-in potential values, how the slope is related to this we can say ND kind of a thing. You must have seen these kind of questions. They are most commonly asked in the competitive exams as well. So you can say in this doping profile over here, from this you can clearly see that since this depletion width is very less in this P side, and this P side is highly doped, uh, and you can clearly see this P side is highly doped, and since this Na concentration is very large as compared to the Nd, and as a result of which we will be having lesser depletion width on the P side, and we will be having more depletion width on the X side, because it is relatively lightly doped when compared to the P side. So if we solve for this thing, if we solve for the Poisson equation, and first if we solve for the from the Gauss law, and then when we solve from the Poisson equation, we will obtain that This material also has this depletion width, which depends on the applied bias and the built-in potential. So this depletion width, as you must have you can say gone through in the lectures, that this depletion width, there is another thing that has been given in this problem. Okay, also, first of all, we need to find the value of ND. Okay, for this problem, we need to find the value of ND. So there is another thing that is also given. Is this what I was saying, that I have done measurements for the capacitance for different voltage values, and I have been given some intercept over here. This intercept over here is minus 0.725 volts. Since this is voltage scale, this will be in volts. So what is the significance of this intercept? These kind of plots, you must see that diode data sheets. You must have gone through those diode data sheets. You must have seen that we have been given some plot, or we have been given some kind of a thing where it is given that this is the intercept, or this is this kind of a thing. And whenever we see those things, we should be able to interpret physically how these things are related to the, for example, built-in potential, for example, doping, for example, in case of, for example, MOSFET or MOSFET, the thickness of the oxide, like that kind of a thing, or the VFB, that is the flat band voltage or the threshold voltage of the MOSFET kind of a thing. So let's not go into the MOSFET at this stage. Let's just simply stick to this problem where this capacitance is a linear equation. This 1 by C square was a linear function of voltage. So this material over here, it says that when I solve for this, wait a second, when I solve for this PN junction, when I solve for this PN junction, I would simply obtain this XD, which is the depletion width. You must have seen in the lectures this depletion width, XD or WD, depletion width, is simply equal to 2 times epsilon naught into epsilon r, which is epsilon naught into epsilon r VBI plus VR by Q times 1 by Na plus 1 by Nd. This whole thing will be under square root. Okay, you must have previously you must have seen this similar kind of a relation in the metal semiconductor junction. Now instead of metal on the left hand side, I am having p-type material. This is the only difference. So this for this p junction, for example, this for this p plus n junction, you can say that this, since this this doping of this Na, since this Na is much greater than Nd, I would say this expression over here would simply be Na plus Nd. This expression would simply be Na into Nd. But this Na is much greater than Nd. It would simply be Na divided by Na Nd. So this Na and Na will go. I will be left with 1 by Nd simply. So this WD or this XD is simply 2 times epsilon naught epsilon r for this heavily doped P plus N junction, VBI plus VR by Q and D. So this is simply the, what we can say, this depletion width. Now going back or backtracking the same problem that we had seen previously, what we can say that this WD, this capacitance, now this capacitance this time is not per unit area, it is the this time capacitance, this is not the total capacitance, sorry, it is a capacitance per unit area. This junction capacitance is simply now epsilon naught epsilon r, or simply epsilon s. This can simply be written by epsilon s by WD, or simply I am just using this formula epsilon A by D. This is the capacitance, this is the distance between the two plates, A is the area. Now since it is the per unit area, it would simply be capacitance per unit area would simply be equal to epsilon naught by d. Okay, so it is simply now the Cj is epsilon naught epsilon r by 2 times epsilon naught epsilon r Vbi plus Vr, and this is q times nd square root, or simply it would be q times nd epsilon naught epsilon r under the square root divided by 2 Vbi plus Vr. This is the Cj, and 1 by Cj square is simply equal to 2 times what I can say Vbi divided by q times nd epsilon naught epsilon r plus 2 times Vr. Now simply from this intercept it means that this intercept, if I say this intercept, look at this intercept, I have to put this 1 by cj square to be equal to 0, and when this 1 by cj square is equal to 0 from this intercept, I would say 1 by cj square is 0 from figure, so it implies vbi is equal to minus Vr at that point, minus Vr dash. So Vbi is simply equal to minus this voltage, minus 0.725. Minus of minus 0.725 is simply plus 0.725 volts. So this is the Vbi, this is the built-in voltage for this PN junction that we have found. Now this was one performance or one device metric that we found out by using the measurements that we had done on the capacitance and voltage relationship. Now for the another I would simply say this Vbi is equal to 0.75. This thing over here 2 by q and d is the slope. Okay, so it is the slope kind of a thing. So slope is simply equal to 2 by q times nd epsilon naught epsilon r. Okay, so it simply means this nd is 2 times q times epsilon naught epsilon r into slope. So for this we must know the value of slope, and the value of slope is going to be equal to this thing 6.15 into 10 raised power of 15 farad per centimeter square. It's 1 by, and then taking its inverse with the voltage, sorry, not its inverse, so its unit says that farad per centimeter square raised power minus 2 volt raised power minus 1. So this is the slope that we have been given. Now if I put it over here, I would wait a second. Okay, so I will be having this to be equal to 2. Q is 1.6 into 10 raised power minus 19. Epsilon naught is 11.7, I guess. Sorry, epsilon r is 11.7 and epsilon naught is 8.85 into 10 raised power of minus 14 farad per centimeter, and this value is equal to 6.15 into 10 raised power 15 into 6.15 into 10 raised power 15, and from this I can get the value of the slope. So since this does not look that much calculation intensive, 1.6, 11.7, 8.85 into 6.15, 1.018, 2 divided by 1.018, 1.96 into 10 raised power 15, 1.96 into 10 raised power 15 centimeter cube. So this is the value of nd that we have obtained for this question. So this is what we were required to find, I guess. So yes, we were required to find the value of nd. So we have obtained the doping concentration. Wait a second. So we have obtained the doping concentration for this n-type material. Sorry, for this p-n junction, not n-type material. So as a result of this thing, we have been asked to do some other stuff in problem 2. The problem 2 says that we have to find the concentration of the acceptor atoms. Since this plot clearly shows that we have the acceptor impurities on the p side and the donor impurities on the n side, as a result of which now we have been told to obtain this acceptor impurity concentration as well. Now we know this built-in potential. You must have solved it while uh, learning the p-n junction while going through the lectures. So it is simply kT by q ln of Na Nd by Ni square. Okay, so it is simply equal to this thing. So let's check whether we have been given Ni, otherwise we have to assume it. Okay, there is no information about Ni. So let's take it, since it is silicon, let's take it 10 to the power of 10 approximately. So it would simply be, this thing will be Vbi by kT into Q, and if I take exponential on both sides, it will be exponential of this thing. It would be Na, this would be Ni square by Nd. This will be the expression for the Na. Absolutely, yes. Yes, this will be the expression for this Na. So Ni square, let's take it to be equal to 10 to the power 10 centimeter cube. Exponential of Vbi was 0.725, I guess. 0.725. We obtained it to be equal to 0.725. 0.725 divided by 0.026, since it is at 300 Kelvin. So this is kT by q, and d came out to be equal to, wait a second, 1.95 into 10 raised power 15. 1.95 into 10 raised power of 15 per centimeter cube. This is the value for Na. So let me solve for this. Exponential of 0.725, wait a second, divided by 0.026, okay, into, so it is 1.2 into 10 raised power 12. So it is 12, and it would go with this thing 10 raised power minus 3, 10 to the power 20. 10 to the power 20 will go with 10 to the power minus 3, and it would be 1.2886. It would be 1.2886 divided by 1.95. It is coming out to be equal to it is coming out to be equal to, wait a second, 27, wait a second, let us do it again, or let me skip this calculation because this exponential is creating problem. It is 27.88, exponential of 27.88, exponential of 27.88. So it is 1.1234567891112. Okay, 1 2 3 4 5. It is 1.282 into 10 raised power 12. Yes, it's 10 raised power 12 into 10 raised power 20. Okay, divided by 1.95 into 10 raised power of 15. So it is 10 raised power of 32. It is 10 raised power of 32. 32 minus 15 is 10 raised power 17. 10 raised power 17 into 1.282 divided by 1.95. It is 0.65 it's coming out to be equal to 0.65 into 10 raised power 17, and I guess no option is matching R. So yes, option D is matching, so we will go with this option D. So let me check if Ni square Ni equal to 1.5 into, what we can say, 1.5 into 10 raised power 10 must have been the option for this. So it would be 1.5 into 1.5, it is 2.25 into 0.65. So you can say that if I take this value of Ni to be equal to 1.5 into 10 raised power 10, because it has not been mentioned in the problem what is the value of Ni. So I can take both of the values are acceptable, 1.5 into 10 raised power 10 and 1 into 10 raised power 10. So if I take it to be equal to 1.5, then it approximately comes out to be 1.46 into 10 raised power 17. So it might be true that this option A can also be close to this thing. If we have done all the calculations properly, that I assume we have done, but if it is the case, then Ni equal to 1.5 into 10 raised power 10 is also not matching the options. So because it's coming out to be equal to 1.46 into 10 raised power 17, so we will be selecting the option D. Neither Ni equal to 10 to the power of 10 nor the 10 to the 1.5 into 10 to the power 10 is matching any option. So this is it about the problem session for today. So if you have any question, you can ask. Otherwise, we can start with this PN junction again in the next lecture, where we will deal more into the problems that are related to this PN junction, and we will solve for the, what we can say, the circuit from the circuit. Okay, I will share, and we will see how these diode or these PN junctions can be used in the circuits as well in the next, we can say, next lecture of ours. So hopefully, if we have no question apart from question in the chat that we have to share this PPT, okay. Apart from this, if we have no question, we can end the session. So let me wait if there is any question. Okay, you can leave if you have no question. Okay, thank you, Lakshmana. No problem. You can attend the second session as well. It is from 5 to 7 today itself, uh, and you can get your concepts more clarified in that session as well. You can use the other link which has been emailed to you today itself. You can join that session. I will share the session's PPT as well, but I request you to join the other session as well. So okay, fine. So I guess we are having no questions, and the people in the meeting are not responding. So let's end this meeting. I will remove all the people from the call. Thank you for attending the session.